The cosmos holds patterns so strange they seem almost intentional. Carl Sagan once reflected that the universe seems neither benign nor hostile, merely indifferent, yet these cosmic coincidences suggest a deeper order. We will explore 29 of the most surprising alignments and anomalies that science simply cannot explain. By the end, you will see the night sky not as a random scatter of lights, but as a tapestry of profound mysteries. Why does the moon perfectly block the sun during an eclipse? What colossal, unseen force is pulling entire galaxies toward it? This journey reveals how each unexplained phenomenon chips away at our current reality. What do you believe is waiting for us in the great unknown? A total solar eclipse is one of the most arresting sights in all of nature. For a few fleeting minutes, day turns to an eerie twilight, the air grows cold, and the sun becomes a perfect black disk wreathed in a shimmering, ethereal corona. This spectacle is only possible because of a numerical fluke so precise it defies belief. The sun's diameter is roughly 400 times larger than the moon's. Yet the sun also happens to be almost exactly 400 times farther away from Earth. This perfect ratio makes the two disks appear the same size in our sky, allowing the moon to block the sun's blinding surface with stunning accuracy. Astrophysicist Neil deGrasse Tyson often points out that we live at the only time in Earth's history where this is possible. The moon is slowly, inexorably drifting away from our planet. In the distant past, it was too close and would have completely obscured the corona. In the far future, it will be too far away to cover the sun entirely, and total eclipses will vanish from our world. This perfect alignment is a temporary gift, a celestial window that just happens to be open for humanity. The mechanics of this dance are governed by elliptical orbits, meaning the apparent sizes of the sun and moon shift slightly. Sometimes the moon is a bit too far away to cover the sun completely, resulting in an annular eclipse, a ring of fire in the sky. But when the alignment is just right, we get the totality that has stopped armies, inspired prophecies, and provided crucial tests for Einstein's theory of relativity. Is this perfect celestial symmetry a mere product of random chance, a fleeting accident in a vast and indifferent cosmos? Or does its profound beauty hint at a deeper, more intricate design woven into the fabric of the universe? This first great coincidence pulls our gaze upward, forcing us to question what other impossible-seeming alignments might be waiting in the dark. From the perfect symmetry of an eclipse, we turn to a pattern of breathtaking beauty written across the cosmos itself. A spiral galaxy like our own Milky Way is a natural masterpiece, its arms unfurling in a sweeping curve that echoes the elegant spiral of a nautilus shell or the seed arrangement in a sunflower. This is no mere artistic fluke. It is a profound mathematical coincidence, a cosmic signature that points to a deep, underlying order. The pattern governing these celestial forms is the Fibonacci sequence, a string of numbers where each one is the sum of the two before it. 1, 1, 2, 3, 5, 8, 13, and so on, stretching into infinity. This sequence produces a special ratio, approximately 1.618 to 1, known as the golden ratio, which appears throughout the natural world with stunning frequency. Mathematicians and astronomers alike have been captivated by the realization that the majestic arms of spiral galaxies often expand outwards, tracing a logarithmic spiral that adheres remarkably closely to this same Fibonacci ratio. It is as if the universe itself is counting. The influence of this ratio on galactic shape is deeply tied to the forces that build these colossal structures. As a galaxy rotates, its stars and gas clouds do not move in unison like a rigid wheel. Instead, the inner regions orbit faster than the outer ones. This differential rotation, combined with the immense gravitational pull of dark matter that we cannot see, shears and stretches the galactic material, winding it into those iconic spiral arms. The resulting pattern is not a perfect Fibonacci spiral, but the resemblance is uncanny and far too close to dismiss as mere chance. Telescopes like the Hubble Space Telescope have provided us with stunning confirmation, capturing countless distant galaxies where this graceful, mathematical form is on brilliant display. Early astronomers who first noticed this pattern were stunned, sparking intense debates about the nature of universal constants. Was this a hint that the same simple rules governing the growth of a fern frond on Earth also governed the birth of a galaxy a billion light-years away? This leads us to a truly mind-bending question. Is mathematics merely a human invention, a tool we use to describe the world? Or is it, in fact, the native language of the cosmos, a fundamental code woven into the very fabric of space, time, and creation? The appearance of this ancient sequence in the grandest structures we know forces us to wonder what other numerical secrets the universe is keeping. That same mathematical order, found in the spirals of galaxies, is mirrored in the very rhythm of life on our own world. We mark the passage of time by the gentle turn of the seasons, the predictable shift from spring's bloom to summer's warmth, then to autumn's chill and winter's quiet. This reliable cycle is what makes our planet a home, and it is governed by a single, delicate feature, the tilt of Earth's axis. Our planet does not spin upright, but leans at an angle of approximately 23.5 degrees. This tilt is the reason we have seasons at all, as different hemispheres receive more direct sunlight throughout the year. But the true cosmic coincidence is not the tilt itself, but its remarkable stability. For millions of years, this angle has wobbled only very slightly, maintaining a balance that prevents our climate from descending into chaos. Climatologists and planetary scientists point out that this stable tilt, combined with the near-circular shape of Earth's orbit, creates the temperate zones where complex life could take root and flourish. Imagine a spinning top. If its wobble becomes too severe, it will fall over. Earth is like a perfectly balanced top, its gentle, predictable wobble giving us the seasons we know. This wobble is part of a much longer cycle called precession, where the direction of Earth's tilt slowly traces a circle in the sky over a period of 26,000 years. There are also slower cycles known as Milankovitch cycles, which subtly change the shape of our orbit and the degree of our tilt over tens of thousands of years. These tiny variations are enough to nudge the planet in and out of ice ages, showing just how sensitive our climate is. But overall, the system is held in a stable equilibrium, a gift of celestial mechanics. To understand how precious this stability is, we need only look to our neighbor, Mars. The red planet lacks a large moon to stabilize it, and its tilt can swing wildly over millions of years, from as little as 15 degrees to as much as 35 degrees. Such dramatic shifts would cause climate catastrophes on Earth, turning our familiar seasons into a turbulent and unpredictable nightmare. Our own history is a testament to the gift of a stable tilt. It was this reliability that allowed early human civilizations to observe the heavens, predict the changing seasons, and develop agriculture. They learned to plant and harvest in sync with a cosmos they could depend on. What if Earth's tilt were just a few degrees different? A smaller tilt would lead to weaker seasonal contrasts, potentially stalling the atmospheric currents that distribute heat and moisture. A greater tilt would bring ferociously hot summers and brutally cold winters, making the development of stable ecosystems, let alone civilizations, nearly impossible. This fine-tuned stability is not just a backdrop for life, it is a fundamental requirement for it. The fact that our world spins at just the right angle and has maintained that angle for so long feels like more than mere luck. It feels like a setting carefully calibrated within a much larger and even more mysterious cosmic system. That stable, life-giving tilt of our world exists within a cosmos born from unimaginable violence. Rewind time nearly 14 billion years to a moment when the entire universe was compressed into a searing, dense inferno of energy and fundamental particles. This was the Big Bang, and for hundreds of thousands of years, the universe remained so hot that light itself could not travel freely. It was a blinding, opaque fog of plasma. When this primordial fireball finally cooled enough for the first atoms to form, light broke free on its epic journey across space. That first flash of light is still with us today, stretched and cooled by the universe's relentless expansion into a faint, cold whisper of microwave radiation that uniformly bathes the entire cosmos. This is the cosmic microwave background, and its existence is the most powerful evidence we have for the Big Bang. But its most baffling feature is not that it exists, it is its incredible, almost perfect smoothness. No matter which direction you look in the sky, the temperature of this background radiation is the same too within a staggering precision of less than 1 part in 100,000. This is a profound cosmic coincidence that, on the surface, makes no sense. The late, great physicist Stephen Hawking identified this uniformity as one of the most significant puzzles in cosmology. He noted that for two regions on opposite sides of the observable universe to have the same temperature, they must have been in contact with each other, able to exchange energy and reach a thermal equilibrium. But according to the standard Big Bang model, these regions were simply too far apart for light or any influence to have ever reached from one to the other. It is as if you walked into a vast room where hundreds of people you had never met were all holding cups of coffee at the exact same temperature, to the 1,000th of a degree, without ever having spoken to each other. How could this be possible? The most widely accepted solution is a theory known as cosmic inflation. This proposes that in the first fraction of a second after the Big Bang, the universe underwent a brief, exponential growth spurt, expanding faster than the speed of light itself. Before inflation, the entire observable universe was a tiny, subatomic speck, a region small enough for every part to be in causal contact, allowing it to smooth itself out to a perfectly even temperature. Then, in an instant, inflation blew this tiny, smooth region up to a size larger than our entire visible cosmos, locking that uniformity into place on the grandest of scales. This theory does more than just explain the smoothness. It also provides the seeds for all the structure we see today. The same quantum fluctuations that were microscopic before inflation were stretched to astronomical sizes, creating the tiny 1 part in 100,000 anisotropies, or temperature variations, that we can now detect. These minuscule ripples in the fabric of the early universe became the gravitational wells into which matter would eventually fall, forming the vast cosmic web of galaxies, clusters, and superclusters we observe. Space missions like the Planck satellite have provided us with exquisitely detailed maps of this cosmic microwave background. These maps are like baby pictures of the universe, revealing the subtle patterns of hotter and colder spots that are the blueprints for everything. The data from Planck matches the predictions of inflation with remarkable accuracy, solidifying its place as a cornerstone of modern cosmology. Yet, this incredible solution opens the door to an even more mind-bending possibility. If our entire observable universe is just one tiny, smoothed-out bubble that inflated from a minuscule speck, what lies beyond? Could there be an endless multiverse, a cosmic foam of countless other bubbles, each with its own unique physical laws and perhaps even different dimensions? The stunning uniformity we see, a coincidence that allowed our structured universe to form, might be a local artifact, a mere property of our particular bubble. Does the flawless smoothness of our cosmic background point to a universe exquisitely fine-tuned for the emergence of galaxies, stars, and planets like our own? Or are we simply inhabitants of one calm, habitable region in an infinitely vast and chaotic multiverse, a single, stable note in a symphony of cosmic chaos? Hidden within the heart of every atom is a number of immense power and mystery. It is a value so precisely set that the slightest deviation would unravel the fabric of reality as we know it. This is the fine structure constant, a fundamental physical constant that governs the strength of the electromagnetic force, the very glue that holds atoms and molecules together. Imagine a cosmic control panel with a dial for this force. Turn it just a fraction of a percent in either direction, and the consequences would be catastrophic. A slightly stronger electromagnetic force, and atomic nuclei repelling each other, would prevent stars from ever forming. A slightly weaker one, and atoms could not bond to create the complex molecules that are the building blocks of life. The universe would be a barren sea of hydrogen or a formless plasma, utterly incapable of supporting the complexity we see around us. The constant is approximately equal to 1/137, a seemingly random number that has captivated and confounded physicists for generations. The legendary Richard Feynman called it one of the greatest damn mysteries in physics, a magic number that comes to us with no understanding by man. You might ask why this number, 1/137, why not 1/136 or 1/138? We do not know. This constant appears in the equations describing how light and matter interact. It dictates the specific colors of light that atoms absorb and emit, the very fingerprints that allow astronomers to identify elements in distant stars. It controls the energy levels within an atom and determines the strength of the chemical bonds that form between them. Without its precise value, the periodic table of elements would be meaningless, and chemistry as we know it would not exist. The quest to understand this number has led scientists to search for any variation in it across the vastness of space or over cosmic time. Using incredibly precise observations of light from the most distant quasars, they have scrutinized the atomic spectra from billions of years ago, looking for any hint that the constant might have been different. So far, the evidence suggests it has remained unchanged, a fixed rule written into the cosmos. This astonishing precision forces us to confront a monumental question. Is the value of the fine structure constant a random, lucky accident in a universe that just happens to be suitable for us? Or is it a necessary consequence of a deeper, more profound theory of everything that we have not yet discovered? Some have pointed to the Anthropic Principle, the idea that the universe must have the properties it does because we are here to observe it. In a multiverse of countless universes, each with different physical constants, we naturally find ourselves in one of the rare ones where the numbers are just right for life. Yet for many scientists, this feels like an incomplete answer. They continue to search for a fundamental reason, a mathematical derivation that would explain why the constant must be 1/137, a reason rooted in the inherent geometry of reality itself. Every high-precision experiment in quantum mechanics, from measuring the magnetic properties of electrons to testing the predictions of quantum electrodynamics, relies on the unwavering stability of this number. Its fingerprints are on every chemical reaction, in every beam of light, in the very structure of your own body. The fact that such a delicate balance exists at the very core of physical law feels less like a coincidence and more like a signature. What other numerical secrets are embedded in the universe, silently ensuring that the cosmos is not only possible, but also alive? These same fundamental forces that dictate the behavior of atoms also orchestrate the grandest structures imaginable, from the fiery hearts of distant quasars. Quasars are the most luminous objects in the universe, active galactic nuclei powered by supermassive black holes feasting on colossal amounts of gas and dust. They act as cosmic lighthouses, their brilliant beams visible from over 12 billion light-years away, offering us a glimpse into the universe's tumultuous youth. Yet, their distribution across the cosmos holds a secret that has left astronomers deeply unsettled. Instead of being scattered randomly, as our fundamental models of the universe predict, some quasars are aligned in staggering, coherent structures that stretch for billions of light-years. These are not mere clusters, but immense walls and filaments of quasars, arranged in a pattern so vast it seems to defy the laws of probability. The Cosmological Principle, a cornerstone of modern cosmology, states that on sufficiently large scales, the universe should appear homogeneous and isotropic, meaning it should look roughly the same in every direction and from every location. The discovery of these quasar alignments, some spanning more than 4 billion light-years across, directly challenges this foundational assumption. It is as if you scattered a handful of sand across a football field and found the grains had somehow arranged themselves into a perfect straight line. One of the most famous of these structures is the huge LQG, or Huge Large Quasar Group, a collection of 73 quasars so immense that it would take light 4 billion years to travel from one end to the other. When astronomers first mapped its extent using massive sky surveys like the Sloan Digital Sky Survey, the result was met with a mixture of awe and skepticism. The sheer scale of the group seemed to violate the theoretical size limit for cosmic structures, a limit derived from the cosmological principle itself. Researchers who first noticed these patterns described a sense of profound disbelief, watching as their computer simulations of a random universe failed again and again to produce anything of comparable scale. The debates that followed were intense, centering on whether we were seeing a real feature of the cosmos or a statistical fluke, a trick of perspective where unrelated objects simply appear aligned from our particular vantage point. Further observations and more sophisticated simulations have only deepened the mystery, suggesting the alignments are real. These structures appear to trace out the skeleton of the cosmic web, the largest pattern of organization in the universe, where galaxies are strung along filaments of dark matter like pearls on an invisible string. The quasars, with their extreme luminosity, simply illuminate this underlying architecture in the most dramatic way possible. What primordial force could have imprinted such coherence on the infant universe, creating blueprints for structures that would take billions of years to fully form? Could these alignments be the fossilized footprints of sound waves rippling through the dense plasma of the Big Bang, frozen in time and stretched to impossible scales by cosmic inflation? Or do they point to influences from an era before the Big Bang, a physics we have not yet begun to comprehend? The quiet assumption that the universe is fundamentally uniform on the grandest scales is now being called into question by these silent, luminous beacons. What other colossal patterns hidden in plain sight are we only just beginning to see? Deep in the silent expanse beyond Neptune, the Pioneer spacecraft were on a one-way journey to the stars. These robotic ambassadors, having completed their grand tours of the outer planets, were now coasting on momentum alone, their paths predicted with absolute confidence by the laws of gravity. Yet something was wrong. As scientists monitored their faint radio signals over decades, a tiny, persistent mystery emerged. Both Pioneer 10 and Pioneer 11 were slowing down. It was an almost imperceptible deceleration, a force about 10 billion times weaker than the gravity we feel on Earth, but it was constant and entirely unexplained. For years, this Pioneer anomaly represented a ghost in the machine, a subtle tug that seemed to defy everything we knew. NASA engineers and physicists around the world were baffled. They proposed a host of theories, from the mundane to the extraordinary. Perhaps it was the gentle push of leaking propellant, or the gravitational pull of unseen, dark matter clustered near our solar system. Some even dared to suggest it might be the first hint of a modification to Einstein's theory of gravity itself, a new physics manifesting only in the deep, quiet dark. The investigation became a monumental effort in forensic science. Teams meticulously reconstructed every aspect of the spacecraft, building intricate thermal models to account for a much more subtle effect. The leading theory that eventually emerged pointed to heat, not the heat of an engine, but the simple, mundane warmth of the spacecraft themselves. The nuclear power sources and onboard electronics generated heat that was radiated away into space. The key was that this radiation was not perfectly symmetrical. Slightly more heat was radiating from the back of the spacecraft's dish antennae than from the front. This tiny imbalance created a photon recoil, a minuscule push that acted exactly like a constant sunward deceleration. The painstaking process of modeling this thermal recoil finally showed that it could account for almost the entire anomaly, a triumph of careful, patient science over exotic speculation. Yet for some, a sliver of doubt remains. The match, while incredibly close, is not perfect, and the case was further complicated by other missions. The New Horizons spacecraft, now traveling through the same distant realm, has not exhibited a similar deceleration. This discrepancy deepens the puzzle. Was the Pioneer effect truly just a quirky engineering issue, unique to the design of those particular probes? Or could there be a more complex interplay of forces at the edge of our solar system that we still do not fully understand? What if this decades-long puzzle was a faint signal, a hint of unknown gravitational effects that only become noticeable when a spacecraft is far from the sun's dominant influence? The quiet story of the Pioneer anomaly serves as a profound lesson in humility. It reminds us that even with our most precise calculations, the cosmos can still present us with a gentle, persistent nudge, a whisper from the void that there is always more to learn. On a quiet Ohio night in August 1977, a radio telescope known as the Big Ear was silently scanning the sky. It was engaged in the tedious, hopeful work of the search for extraterrestrial intelligence, listening for a whisper in the cosmic noise. Suddenly, the machine registered a signal so powerful and so peculiar that it defied all expectation. It was a narrowband radio burst precisely at the frequency of the hydrogen line, a logical channel for interstellar communication. It lasted for 72 seconds, rising and falling in intensity exactly as a signal from a fixed point in space would as the Earth rotated, painting a perfect curve on the printout. When volunteer astronomer Jerry Amon reviewed the data, he was so stunned he circled the alphanumeric sequence and simply wrote "Wow" in the margin, giving the signal its immortal name. The WOW signal remains one of the most tantalizing and enduring mysteries in the history of astronomy. It came from the direction of the constellation Sagittarius, a region crowded with stars, and then it vanished forever. The signal's characteristics pointed to an origin far beyond our solar system. It was not a repeated transmission, nor was it any known form of human-made interference. It was a one-time cosmic shout, a blip of impossible clarity in an otherwise silent universe. For decades, astronomers have tried to solve the puzzle. They have meticulously ruled out aircraft, satellites, and ground-based transmitters. they have scanned the same patch of sky with more powerful instruments, listening for a repeat performance that has never come. Some propose that it might have been a reflection of a human signal bouncing off a piece of space debris, but the timing and frequency make this incredibly unlikely. Others suggested natural causes, like the emission from a passing comet, but detailed analysis showed no known comets were in that specific area of the sky at that exact time. The very nature of the signal makes it a profound coincidence. It was strong, it was intelligent in its design, and it appeared in a frequency band that is naturally quiet, a window purposefully chosen for interstellar listening. The fact that we happen to be pointing our telescope in that exact direction at that precise moment to catch a 72-second event feels like winning a lottery with odds beyond calculation. This single event became a cornerstone for SETI, inspiring generations of scientists to expand the search. It taught a sobering lesson about the transient nature of cosmic phenomena. The universe might be filled with conversations, but they could be fleeting, like ships passing in the deepest, darkest ocean. Was the wow signal a message intentionally beamed at us, a cosmic hello that we were too primitive to answer? Or was it the death cry of a distant, catastrophic stellar event, a natural radio burst of a type we have not yet classified? The silence that followed is as eloquent as the signal itself. It beckons us to keep listening, to build better ears, and to remain open to the possibility that we are not alone, and that the next great discovery might be another single, brilliant, and unexplained flash in the night. Finding a needle in a cosmic haystack would be a simple task compared to locating another Earth. The sheer volume of stars, the vast distances, and the specific conditions required make the search seem almost hopeless. Yet, one of our nearest stellar neighbors presents a coincidence that reignites that hope entirely. Just 12 light-years away, a journey that is practically next door in galactic terms, sits Tau Ceti, a star so similar to our own sun it has been a fixture in science fiction for generations. The true surprise, however, is not just the star itself, but the worlds we have found orbiting it. Astronomers have identified multiple planets within Tau Ceti's habitable zone, that narrow, life-giving band where temperatures could allow liquid water to pool and flow on a planet's surface. Exoplanet researchers point to Tau Ceti's remarkable stability as a key factor in its potential. The star is quiet, with relatively low magnetic activity, meaning it bathes its planets in a much calmer radiation environment than many other sun-like stars. This reduces the risk of stellar flares stripping away nascent atmospheres, making it one of the most promising targets in our celestial backyard. The very existence of multiple potentially rocky worlds in this temperate region around such a close and stable star feels like more than just luck. It feels like a deliberate clue. Uncovering these distant worlds required a feat of astronomical precision. Scientists used a method called radial velocity, watching for the subtle wobble in Tau Ceti's light caused by the gravitational tug of its orbiting planets. As a planet circles its star, it pulls the star ever so slightly, causing its light to shift in a detectable rhythm. This technique, combined with advanced data filtering to screen out the star's own surface activity, revealed a system of at least 4 planets, with 2 sitting squarely in that precious habitable zone. The challenge now shifts from discovery to confirmation. Determining if these worlds truly have atmospheres and what gases they contain is the next great frontier. The search for biosignatures, like the simultaneous presence of oxygen and methane, which on Earth are clear indicators of biological activity, requires power far beyond our current telescopes. Missions like Kepler taught us that planets are commonplace, filling our catalog with thousands of alien worlds. But Tau Ceti is different. It is not a distant statistical point of data. It is a specific, nearby destination, a system we can study in ever-increasing detail with the next generation of observatories. If life in any form has taken root on a world orbiting a star so close to our own, what would that imply about the vitality of the cosmos? The silence from Tau Ceti is not an emptiness but an invitation, urging us to listen more closely and to look deeper into the familiar suns that share our small corner of the galaxy. Our entire galaxy is caught in a silent, relentless river of motion. The Milky Way, along with its neighboring galaxies, is not drifting aimlessly but is being pulled, as if by an invisible current, toward a specific point in the depths of space, toward the constellation Centaurus. This mysterious destination earned a fittingly dramatic name, the Great Attractor. It represents a staggering cosmic coincidence, a hidden concentration of mass so immense that it tugs on entire galaxies, yet it lies almost perfectly concealed from our view, hidden behind the thick dust and stars of our own galaxy's central bulge. This region is so obscured it falls within what astronomers call the zone of avoidance, a blind spot in our celestial maps. Renowned cosmologists have described this as a fundamental challenge to our understanding of the universe's architecture, forcing us to admit that some of the most significant structures in the cosmos might be lurking in the shadows, completely invisible to our traditional telescopes. The discovery of this pull did not come from a single image, but from the patient mapping of cosmic flows, by meticulously measuring the redshifts of thousands of galaxies, which tells us how fast they are moving away from us due to the universe's expansion. Astronomers noticed a persistent deviation. A vast swath of the local universe, including us, was moving with an extra velocity, a peculiar motion superimposed on the smooth Hubble flow. This anomaly pointed directly toward the hidden heart of Centaurus. It was like watching leaves floating down a river, only to see them all suddenly veer toward a whirlpool you cannot see. Major surveys, like those conducted with the Parkes Observatory in Australia, have worked like cosmic archaeologists, using radio waves to peer through the obscuring dust of the zone of avoidance. These efforts revealed that the Great Attractor is not a single, monstrous object, but a colossal supercluster of galaxies, a gravitational nexus where the threads of the cosmic web knot together. The initial detection of this drift was met with a mix of excitement and profound unease among the astronomers who first charted it. They had found a gravitational anomaly of breathtaking scale, a testament to the fact that most of the universe's matter does not glow. This hidden mass, the dark matter that forms the skeleton of the cosmos, is the true architect of this great flow. Yet, even when we account for the immense mass of the discovered supercluster, the math does not fully add up. The pull seems stronger, hinting that the Great Attractor itself may be just a local manifestation of an even vaster and more distant structure, a gravitational behemoth pulling on the puller itself. What colossal secrets still lie behind the veil of the galactic plane, completely invisible to our eyes? Could the ultimate source of this great river of galaxies reshape our most fundamental understanding of cosmic structure and the distribution of dark matter? This hidden gravitational puzzle reminds us that the universe's greatest dramas are often playing out just beyond our line of sight. That silent, hidden river of galaxies pulls us toward one mystery, while a recent visitor from the void delivered another. In October 2017, astronomers in Hawaii spotted a faint point of light moving at a speed that could only mean one thing: it was not from here. For the first time in recorded history, an object from another star system was caught passing through our own. They named it Oumuamua, a Hawaiian word for scout, and it was unlike anything we had ever seen. Its path was a hyperbolic arc, a single slingshot trajectory around the sun that guaranteed it would never return. It had no visible coma or tail, the telltale signs of a comet. It was dark, reddish, and tumbling through space, but the most profound coincidence was yet to come. As it sped away from the sun, something impossible happened. It accelerated. It was not just coasting on gravity anymore. An unseen force was giving it an extra push. This non-gravitational acceleration was tiny, but it was real, and it defied all simple explanation. The object was shaped like a pancake or a cigar, with estimates suggesting it was perhaps 10 times longer than it was wide. This bizarre form, combined with its mysterious acceleration, sent a ripple of excitement and controversy through the scientific community. Harvard astrophysicist Avi Loeb famously proposed a provocative explanation. Could Oumuamua be a piece of advanced technology, a light sail from an alien civilization? A light sail, much like a boat sail catches wind, is designed to be pushed by the radiation pressure from starlight. Loeb suggested that if Oumuamua was an extremely thin, lightweight object, the gentle pressure of sunlight could account for its strange acceleration as it moved away from our sun. This was not a claim of certainty, but a challenge to consider all possibilities, no matter how extraordinary. The scientific mainstream scrambled for a natural explanation, and one leading candidate emerged, outgassing. When a comet heats up near a star, ices on its surface turn directly to gas, jetting away like a natural rocket engine. This can provide precisely the kind of non-gravitational push that was observed. The problem was that Oumuamua showed no visible signs of this activity, no dust cloud, no gas tail. This forced theorists to get creative. Perhaps it was made primarily of hydrogen ice. Hydrogen is invisible when it outgasses, and a hydrogen iceberg could explain the acceleration without a visible trail. Yet, the survival of a fragile hydrogen object on an interstellar journey remains hotly debated. The mystery deepens when we compare Oumuamua to our second known visitor, Comet Borisov, which arrived 2 years later. Borisov was unmistakably a comet. It had a brilliant tail and a clear coma, behaving exactly as scientists expected. The stark contrast between the two highlights Oumuamua's profound strangeness. Was it a rare type of asteroid, a comet that had been baked solid over eons, or something else entirely? The event was a wake-up call. It proved that interstellar objects are real and that they are passing through our solar system with some frequency. This single, enigmatic scout has since spurred a new branch of astronomy with projects like the Vera C. Rubin Observatory being designed specifically to scan the skies for more of these fleeting visitors. They represent pristine pieces of other star systems, offering us a chance to study the chemistry and formation of distant worlds without ever leaving our own. So, what did we truly witness? Was Oumuamua a bizarre but natural shard of planetary debris ejected from a faraway solar system, a cosmic iceberg venting invisible gas? Or was it, as some still wonder, a relic of a technology beyond our own, a silent, discarded artifact drifting on the cosmic currents? Its brief passage forces us to look up and wonder about the endless diversity of travelers in the dark and what the next one might reveal. Building a ladder to the stars requires absolute precision, with each rung perfectly calibrated to support the next. This is the cosmic distance ladder, a sequence of measurement techniques that allow us to chart the vast expanses of the universe. The profound coincidence is that methods as different as simple geometry and the physics of stellar explosions all converge on a remarkably consistent picture of cosmic distances and the universe's expansion rate. Yet, a subtle but persistent crack in this ladder is threatening to shake the very foundations of cosmology. Nobel laureate Adam Rees, whose work on supernova revealed the accelerating universe, describes this discrepancy as the Hubble tension. It is a stubborn puzzle where measurements of the universe's current expansion rate, the Hubble constant, do not quite agree with predictions based on the ancient light from the Big Bang. How can our most trusted tools for mapping reality be giving us conflicting answers? The first rung of the ladder is stellar parallax, a method as straightforward as holding your thumb out and closing one eye at a time. As Earth orbits the Sun, the apparent shift in position of a nearby star against the distant background allows us to calculate its distance through pure trigonometry. This gives us our most direct and reliable measurements for the closest stars, forming the unshakable base of the ladder. With these nearby stars secured, we can climb to the next rung, a class of stars known as Cepheid variables. These are cosmic lighthouses with a regular pulse. Their intrinsic brightness is directly tied to their pulsation period, a relationship discovered by Henrietta Leavitt. By observing how long a Cepheid takes to brighten and dim, we know its true luminosity. Comparing that to how dim it appears from Earth gives us its distance with stunning accuracy. Cepheids allow us to reach out to nearby galaxies, calibrating the ladder for the next, even more powerful step. That crucial step involves Type Ia supernova, the thermonuclear explosions of white dwarf stars. These events are so brilliant and so uniform in their peak brightness that they act as standard candles, visible across billions of light years. By identifying these supernovae in galaxies whose distances we already know from Cepheid variables, we can precisely calibrate their true power. Once calibrated, we can find a Type Ia supernova in a galaxy far, far away, measure its apparent brightness, and instantly know its distance. This is how we measure the expansion rate of the universe itself. We combine these supernova distances with measurements of the host galaxy's redshift, the stretching of its light toward longer, redder wavelengths caused by the expansion of space. The greater the redshift, the faster the galaxy is receding from us. By plotting distance against recession velocity for thousands of galaxies, we derive the Hubble constant, the number that tells us how fast the universe is expanding today. The tension arises because this locally measured value, championed by teams like Reese's, is slightly faster by a few percent than the value predicted from the pristine snapshot of the early universe, the cosmic microwave background. The early universe measurement, made with exquisite precision by the Planck satellite, is a prediction of what the Hubble constant should be today based on the standard model of cosmology. The fact that the local measurement is different is like checking the time on two perfectly engineered clocks, one set at the dawn of time and one set today, and finding they tick at a slightly different pace. This is not a simple error. Teams have checked and rechecked their work using different telescopes, different stars, and different supernova. The discrepancy persists. Does this mean our standard model of cosmology, which includes dark matter and dark energy, is incomplete? Could there be an unknown form of energy that briefly flared up in the universe's adolescence, giving expansion an extra kick? Or are we seeing the subtle influence of exotic new particles that altered the early universe's evolution? Perhaps the simplest explanation is the most profound, that we are being humbled by our own perspective, and that some unknown systematic error, some tiny miscalibration in our magnificent ladder, is creating a phantom tension. This harmony of measurements, so precise yet so dissonant, does not signal a failure of science but a frontier. It is a quiet signal from the cosmos that our map of reality, for all its detail, may still be missing a few essential contours. What new physics is waiting to be discovered in the space between two conflicting numbers? Our planet's journey is more than a simple circle around the Sun. Every 225 to 250 million years, our entire solar system completes a single, grand orbit around the center of the Milky Way. This vast span of time is known as a galactic year, a cosmic heartbeat measured not in seasons but in epochs, and there is a chilling coincidence buried in the rock beneath our feet. Some of Earth's most devastating mass extinctions appear to pulse in a rhythm eerily close to this galactic cycle. The Great Dying, the Permian Triassic extinction that wiped out nearly all life on Earth, and the later Cretaceous Paleogene event that ended the reign of the dinosaurs, are two cataclysmic points that seem to align with this immense clock. Paleontologists and astronomers studying this pattern ask a startling question. Could the very structure of our galaxy be a silent conductor of life and death on our world? The leading theory points to a gravitational domino effect. As our solar system travels through its orbit, it does not move on a flat, even plane. Instead, it bobs up and down, periodically passing through the crowded, dense spiral arms of the Milky Way. These spiral arms are not just collections of stars, they are regions of intensified gravitational turbulence. Each time the solar system plunges into one of these arms, its gravitational field experiences a subtle but significant shake. This jostling can dislodge countless icy bodies in the distant Oort cloud, a vast spherical shell of frozen remnants at the very edge of our solar system. The result is a dramatic increase in the number of comets nudged onto perilous sunward paths, a cosmic shower that can last for millions of years. The evidence is etched in both stone and sky. Detailed analyses of the fossil record reveal a pattern of biodiversity loss that some scientists argue repeats every 26 to 30 million years, a timescale that fits neatly within the broader galactic year. Furthermore, the ages of large impact craters on Earth also show a possible periodicity, with clusters of impacts occurring at intervals that match these proposed comet showers. It is as if a celestial metronome has been ticking for billions of years, its quiet beat occasionally triggering a global winter. The debate over this cyclical causality is intense. Skeptics rightly point out that correlation is not causation, and the geological record is an imperfect book with many missing pages. Not every extinction event aligns perfectly with the proposed cycle, and other terrestrial causes, like massive volcanic eruptions, clearly play a dominant role. Yet, the statistical signal is persistent enough to keep the idea alive and compelling. It forces us to widen our perspective from Earth's biosphere to the entire galactic environment. Our planet is not an isolated island, but a ship sailing through a cosmic sea that has its own currents and storms. The gravitational tides of the galaxy itself may subtly influence the climate and the very frequency of life-ending impacts. Is the history of life on Earth subject to rhythms set by our galaxy's slow, majestic dance? Does the Milky Way, in its silent rotation, hold a faint but real influence over which species thrive and which vanish forever into stone? This cyclical connection between the galactic year and terrestrial destiny invites us to look for other, even grander, temporal coincidences written into the fabric of space and time. For 23 days in late 2003, the Hubble Space Telescope did something that seemed almost pointless. It fixed its gaze on a single, seemingly empty patch of sky near the constellation Fornax, a region so dark it was equivalent to looking at a grain of sand held at arm's length. It gathered every faint photon of light it could, and when the final image was processed, it revealed a view that forever changed our cosmic perspective. That tiny, dark spot was not empty at all. It was filled with a breathtaking tapestry of light, a deep space mosaic of nearly 10,000 distinct galaxies, each a swirling island of billions of stars. This was the Hubble Ultra Deep Field, and it gave us our first realistic census of the cosmos. Astronomer Garth Illingworth, a key figure in the project, described it as looking back through time, seeing galaxies as they were just a few 100 million years after the Big Bang. The staggering coincidence lies in the final count. When scientists extrapolated from this single, minuscule frame to the entire observable universe, they arrived at an estimate of roughly 2 trillion galaxies. This number, almost too vast to comprehend, aligns almost perfectly with the predictions of our best theoretical models of cosmic structure formation, a profound convergence of observation and theory that validates our entire understanding of the universe's history. This alignment is not just a numerical fluke, it is a direct window into the role of dark matter, the invisible scaffolding of the cosmos. In the early universe, tiny ripples in the density of dark matter, imprinted by inflation, began to pull normal matter, the baryons, into their gravitational grasp. These dark matter halos acted as cosmic cradles, gathering gas and dust until they were dense and hot enough to ignite the first stars, birthing the very galaxies we see in the ultra-deep field. The predicted number of these halos matches the number of galaxies we observe, a beautiful confirmation that dark matter's hidden architecture is the true blueprint for everything we see. The story did not end with Hubble. The James Webb Space Telescope has since peered even deeper into that same patch of sky, its infrared eyes capable of seeing through the cosmic dust that shrouded the universe's first light. JWST has uncovered a population of galaxies even more ancient and numerous than Hubble could detect, galaxies that formed shockingly early and are surprisingly mature. These new observations are already challenging and refining our models of how the very first structures assembled in the dark ages of the universe. This cosmic census also plays a crucial role in solving one of astronomy's most persistent puzzles, the missing baryon problem. We can calculate how much normal matter should have been created in the Big Bang, but a vast portion of it seemed to be unaccounted for. The immense number of galaxies revealed by the ultra-deep field and subsequent surveys points to a solution. A significant fraction of these missing baryons is likely tied up in the vast, hot halos of gas that surround each and every galaxy, a faint, diffuse atmosphere that is incredibly difficult to detect but contains more mass than all the stars within the galaxy itself. So we are left with a number that is both an answer and a question: 2 trillion galaxies, with each one hosting billions of stars, and many of those stars likely harboring planets. The sheer statistical abundance is overwhelming. How many worlds orbit within those 2 trillion islands of light? How many shores might be washed by alien seas? The Hubble ultra-deep field did not just fill a dark spot in the sky. It filled our imagination with a scale of possibility that forever redefines our place in the cosmos. The universe is not a uniform sea of light, but a cosmic sponge riddled with immense dark bubbles. Between the luminous filaments of the cosmic web lie the voids, incomprehensibly vast regions of near-nothingness. The 15th coincidence is the staggering scale of these empty spaces, and the profound questions their existence raises about the very nature of our cosmos. One of the largest and most famous is the Boötes Void, a spherical chasm so enormous that it would take light 250 million years to cross it. If our Milky Way sat at its center, we would have had no knowledge of other galaxies until the 1960s. The void is not completely empty, but it contains only a few dozen galaxies, where a typical region of that size should host thousands. This profound emptiness is a coincidence that challenges our most sophisticated simulations of the Big Bang. Cosmologists who run these virtual universes find that while voids do form, they rarely grow to the staggering proportions of the Boötes Void. Its existence suggests that the initial distribution of matter in our particular universe may have been far more lumpy. or that processes we do not fully understand allowed these voids to empty and expand beyond expected limits. The story of its discovery is a lesson in cosmic humility. In the 1980s, astronomers were mapping the large-scale structure of the universe when they stumbled upon this gaping hole in the constellation of Boötes. The initial reaction was disbelief, a suspicion that their observations were flawed or that intervening dust was obscuring the view. But repeated surveys confirmed the void was real, a true desert in the celestial landscape. These voids are not static. They are dynamic entities, expanding faster than the universe average because their feeble gravity cannot compete with the overall cosmic acceleration. The space within a void is, in a very real sense, being stretched more aggressively. This has a direct, observable consequence known as the integrated Sachs-Wolf effect. As light from the cosmic microwave background travels through these vast, evolving, empty regions, it gains a tiny amount of energy, leaving a specific, cold imprint on the background radiation map. This subtle signal is a direct fingerprint of dark energy at work, a measurement of how the energy of empty space itself is pushing these voids to grow ever larger. Major sky surveys like the Sloan Digital Sky Survey have become our cartographers of nothingness, meticulously mapping the distribution of millions of galaxies to reveal the full, bubbly architecture of the cosmos. They show a universe where voids make up the majority of the volume, with galaxies merely clinging to the thin, bright walls between them. What primordial seed gave rise to such an immense emptiness? Are these voids simply accidental gaps in the cosmic lottery, the natural outcome of gravity pulling matter into clusters and leaving behind deserts? Or are they the magnified signatures of primordial quantum fluctuations, tiny random wrinkles in the fabric of the newborn universe that inflation stretched to these impossible scales? This profound emptiness is not an absence of story, but a presence of mystery, a silent, expanding sphere that forces us to question the very architecture of space and the forces that sculpted it from the quantum foam of creation. Deep within the heart of our sun, a silent, ghostly exodus is always underway. Countless trillions of neutrinos, ethereal particles born from the nuclear fires that power our star, stream outward in all directions, passing through the entire body of the Earth as if it were not even there. For decades, physicists believed these phantoms were massless, fleeting travelers, behaving precisely as the standard model of particle physics dictated. But the universe had a surprise waiting. Experiments designed to catch these solar neutrinos were coming up short, detecting only about a third of the number predicted by our most robust solar models. The answer to this solar neutrino problem was not a flaw in our understanding of the Sun, but a fundamental revolution in our understanding of the particles themselves. Neutrinos were not simply vanishing, they were shape-shifting. On their journey from the solar core to our detectors, they were oscillating, changing between three distinct flavors: electron, muon, and tau. This discovery of neutrino oscillation, which earned Takashi Kajita and Arthur B. McDonald the Nobel Prize, was earth-shattering. It meant that neutrinos must have mass, however tiny, a fact that flatly contradicted the original, pristine standard model. The mechanics of this oscillation are a delicate quantum ballet. A neutrino is not purely one flavor, but exists in a constant, probabilistic superposition of all three. As it travels through space, the quantum phases of its mass states evolve at slightly different rates, causing its flavor identity to oscillate in a regular, predictable rhythm. The probability of detecting a specific flavor depends on the distance the neutrino has traveled and the energy it carries, a phenomenon confirmed with stunning precision by instruments like the Super Kamiok and detector in Japan, a colossal tank of ultra-pure water buried deep underground. This revelation opens a portal to deeper mysteries. The three known neutrino masses are not fully mapped, leading to the puzzle of the neutrino mass hierarchy. Are the two closest masses lighter or heavier than the third? Determining this ordering is a primary goal of next-generation experiments like the Deep Underground Neutrino Experiment, DUNE, which will fire a beam of neutrinos 800 miles through the Earth from Fermilab in Illinois to a massive detector in South Dakota. By precisely measuring how these oscillations change over such a long baseline, scientists hope to pin down the hierarchy. Even more profound is the hunt for CP violation in the neutrino sector. CP violation is a subtle asymmetry in how particles and their antimatter counterparts behave. Finding it in neutrinos could be the master key to one of cosmology's greatest questions. The Big Bang should have created equal amounts of matter and antimatter, which would have annihilated each other, leaving behind a universe of pure energy. Yet we exist in a cosmos made almost entirely of matter. Could neutrinos, through a fundamental lopsidedness in their oscillations, be the reason? Could they have tipped the scales in the universe's first second, providing the mechanism that allowed a tiny excess of matter to survive and form everything we see? This ghostly particle, so reluctant to interact, may hold the secret to our very existence. Its tiny mass, a mere whisper against the scale of other particles, represents a crack in the standard model, a sign that our map of the subatomic world is incomplete. What other phantoms are dancing just beyond our perception, their subtle rhythms governing the fate of the cosmos? Far beyond the orbit of Neptune, the solar system does not simply end. It gives way to a vast, dark frontier known as the Kuiper Belt, a sprawling disk of icy remnants left over from the planet's formation. Here, in the deep freeze, thousands of small worlds drift in a silent, slow-motion ballet. But this dance is not entirely random. Astronomers mapping these distant orbits have stumbled upon a pattern so peculiar it hints at a ghost in the machine. The most distant Kuiper Belt objects do not scatter randomly across the sky. Instead, their elongated orbits are mysteriously clustered, as if an unseen hand is herding them, guiding their paths through the perpetual twilight. This orbital clustering is a gravitational anomaly that has forced scientists to consider a radical possibility, a hidden giant, a so-called Planet 9, lurking in the solar system's uncharted reaches. Planetary scientists like Konstantin Batygin, who co-proposed the hypothesis, describe the evidence not as a single clue, but as a constellation of them. When they modeled the gravitational influence of a hypothetical planet about 10 times the mass of Earth, orbiting far beyond Pluto, their simulations showed that such a world would naturally shepherd the orbits of the most distant KBOs into the exact alignments we observe. It acts as a massive perturber, its gravity slowly sculpting the orbital fabric of the outer solar system over billions of years. The case rests on the bizarre paths of specific objects. Sedna, a reddish world discovered in 2003, travels on an incredibly elongated orbit that takes 12,000 years to complete, a path that is difficult to explain without the persistent tug of a substantial external mass. Several other extreme trans-Neptunian objects share this strange orbital alignment, their points of closest approach to the Sun, their perihelia, clustered in space, while their orbits are tilted in a similar direction. This is not what you would expect from a calm, undisturbed solar system. The hunt for this phantom world is now a major astronomical pursuit. Researchers are using some of the most powerful telescopes on Earth, like the Subaru telescope in Hawaii, to scan the sliver of sky where calculations suggest Planet 9 might be hiding. The challenge is immense. The object would be incredibly faint and moving very slowly against the background stars. Yet, the potential reward is a redefinition of our own cosmic neighborhood. Not everyone is convinced, of course. Skeptics propose alternative explanations, such as the collective gravitational pull of many small Kuiper belt objects acting together, or perhaps the lingering gravitational imprint of a primordial black hole captured by the Sun long ago. Others suggest that the observed clustering could be an observational bias, a trick of perspective where we have only mapped a small, skewed sample of these incredibly distant objects. But as more of these extreme KBOs are discovered, the statistical case for an unseen perturber grows stronger. So are we on the verge of discovering a new planet in our own backyard, a world so vast it has eluded us until now? Or is this clustering a cosmic mirage, a beautiful pattern born from the limitations of our current data? The silent, icy bodies of the Kuiper belt hold their secrets close, their aligned paths pointing toward a mystery that could reshape our family portrait of the Sun's dominion. Our galaxy's core is not a placid place. It is a cosmic engine of unimaginable power, and we now know it has been blowing smoke. Giant, symmetrical bubbles of high-energy gamma-ray light extend for 25,000 light-years above and below the galactic plane, a discovery that stunned astronomers when the Fermi Gamma-Ray Space Telescope first revealed them. These are the Fermi Bubbles, and their existence points to a cataclysmic eruption from the heart of the Milky Way in our relatively recent cosmic past. The profound coincidence is their near-perfect symmetry and immense scale, a pair of identical lobes that suggest a single, violent event rather than a slow, steady process. Astrophysicists are locked in a vigorous debate over the nature of that event. Was it a past period of intense activity from our supermassive black hole, Sagittarius A star, a phase where it was an active galactic nucleus, or AN, feasting on surrounding matter and firing colossal jets into intergalactic space? Or was it the result of a more gradual process, like a period of frenzied starbirth that produced countless supernovae, their combined shock waves blowing these massive structures out of the galactic disk? The answer lies in the light itself. Gamma rays are the most energetic form of electromagnetic radiation, produced by the most violent processes in the universe. The bubbles glow in this specific light because they are filled with ultra-fast, moving particles, cosmic rays, that slam into the slower moving gas of the galactic halo. These collisions create gamma rays, painting the faint, giant structures that Fermi could see. To unravel the mystery, scientists have turned to multi-wavelength observations. The Planck satellite has mapped a faint microwave haze coinciding with the bubbles, suggesting they are also filled with hot, magnetized gas. X-ray observatories have spotted shock fronts at their edges, the telltale signs of an immense explosion plowing into the surrounding medium. By combining all these observations, researchers can estimate the bubble's total energy content, a staggering equivalent to 100,000 supernova explosions. This immense energy budget strongly favors the black hole hypothesis. It is difficult to imagine a coordinated starburst producing such a clean, symmetrical, and energetic structure. We see similar, though often more dramatic, lobes and jets erupting from the cores of other galaxies with active supermassive black holes. Our own galactic center appears to have had a quieter history, but the Fermi bubbles are a clear sign that it, too, has experienced violent outbursts. The implications are profound. If our supermassive black hole was active a few million years ago, it would have bathed the entire galaxy in radiation, potentially sterilizing swaths of the Milky Way and influencing the evolution of life on any worlds in its path. This energetic phenomenon forces us to see our galaxy not as a static collection of stars, but as a dynamic, evolving entity with a violent heartbeat. Did a single, colossal belch from Sagittarius, a star, create these immense structures? And if so, what awakened the sleeping giant? The silent, glowing bubbles above us are a permanent monument to a forgotten cataclysm, a clue to the turbulent life cycle of our own cosmic home. A galaxy's redshift is its cosmic fingerprint, a measure of how fast it is receding from us in an expanding universe. We expect these redshifts to be as random as the galaxies themselves, a smooth and continuous distribution across all possible values. Yet, when some astronomers began plotting these numbers, they found something deeply unsettling. The redshifts were not random at all. Instead, they appeared to cluster at specific, preferred values, as if the cosmos were quantized, ticking like a cosmic clock set to a rhythm we cannot hear. This is the controversial claim of redshift quantization, a pattern that, if real, suggests the universe possesses a vast, lattice-like structure. The late astronomer William Tift first reported this phenomenon decades ago, meticulously analyzing the redshifts of galaxy pairs and groups. His data seemed to show that redshifts were not arbitrary, but occurred in distinct steps, like notes on a musical scale. Tift proposed that this quantization was a fundamental property of the cosmos, perhaps related to the intrinsic properties of matter or the fabric of space-time itself. His work was met with intense skepticism, as it directly challenged the foundational cosmological principle that the universe is homogeneous and isotropic on large scales. A quantized redshift distribution would imply a preferred direction or a grid-like organization to reality, a notion that many found difficult to accept. The debate hinges on the data and its potential pitfalls. Skeptics, like many mainstream cosmologists, argue that these apparent patterns are almost certainly selection effects. When you observe galaxies, you are not getting a perfectly clean sample. Your data is filtered through the limitations of your telescope, the dust of our own galaxy, and the complex ways galaxies cluster together. These biases can easily create the illusion of patterns in what is actually a random distribution. It is like looking at a handful of pebbles tossed on a beach. The way they land might seem to form a line, but it is just a trick of chance. The statistical analyses are fiercely contested. Some studies of specific galaxy surveys, particularly those looking at pairs of galaxies, have found tantalizing evidence for periodicity in their redshift distributions. Other, more comprehensive surveys have failed to replicate the effect, finding instead the smooth, random scatter that standard cosmology predicts. The case remains open because the signal is subtle and extraordinarily difficult to disentangle from the noise of observational bias. If the universe truly has this hidden lattice, what fundamental physics are we missing? Could it be evidence of a universe with a discrete fabric, where space itself is not infinitely divisible but composed of tiny, fundamental units? Or does it point to a more exotic explanation, such as our universe being a vast holographic projection? This quantization puzzle forces us to question the very smoothness of cosmic expansion, suggesting that other, even more subtle anomalous patterns might be woven into the flight of the galaxies. Galaxy clusters, the most massive structures in the universe, are caught in a silent, coherent river of motion. They are drifting in a specific direction, not just with the universe's expansion, but as if pulled by something immense and unseen that lies beyond the edge of everything we can observe. This is the dark flow, a phenomenon so strange it suggests our entire observable cosmos might be feeling the gravitational tide of something outside it. Cosmologist Alexander Kashlinsky, who led the team that discovered this anomaly, described it as a profound hint that our universe is not isolated, that the domain of existence extends far beyond what we call the observable universe. The detection hinges on a subtle fingerprint in the cosmic microwave background, As the hot gas within these gigantic galaxy clusters moves through space, it scatters the photons of the ancient background radiation. This interaction, known as the kinetic Sunyaev-Zeldovich effect, creates a minute temperature distortion that betrays the cluster's peculiar velocity. By meticulously mapping this effect for over 1,000 clusters, researchers found they were all streaming toward the same distant point at a staggering speed of millions of miles per hour. This coherent motion on such a colossal scale is not predicted by our standard models of cosmic structure and dark energy. It is as if you dropped countless leaves in a calm forest, only to watch them all drift steadily in one direction, pulled by a wind whose source you cannot see. The scientific community has responded with intense scrutiny. Follow-up studies have worked to rule out potential systematic errors, such as imperfections in how we clean the cosmic microwave background maps or local effects from our own galaxy's motion. Some researchers have proposed that the flow could be explained by an immense, previously undetected supercluster of matter, though the scale required would be difficult to reconcile with the overall homogeneity of the universe. Supercomputer simulations of the cosmos, which accurately reproduce the cosmic web of galaxies and dark matter, consistently fail to generate a bulk flow of this magnitude and coherence. The flow persists as a stubborn outlier in our data. Could this motion be the gravitational pull of a concentration of matter so vast it lies beyond our cosmic horizon, in a region of space-time that inflated away from us during the universe's first instant? Or, more speculatively, could we be feeling the tidal tug of another universe entirely, a neighboring bubble in a vast multiverse brushing up against our own? The dark flow does not just point to unseen mass, it points to the unseen architecture of reality itself, inviting us to consider that the greatest forces shaping our cosmic journey may originate from a realm we can never directly see. The first 3 minutes of the universe were a forge of unimaginable heat, a nuclear furnace that fused the primordial soup of protons and neutrons into the first light elements. This process, known as Big Bang nucleosynthesis, was remarkably successful, producing the hydrogen and helium that would become the fuel for all future stars. Yet it left behind a stubborn, precise anomaly. The predicted abundance of lithium-7, the universe's third lightest element, is about 3 times higher than what we actually observe in the atmospheres of the most ancient stars. This is the cosmological lithium problem, a clear crack in our otherwise pristine model of the universe's first moments. Nuclear astrophysicists have been wrestling with this discrepancy for decades, a clear sign that something in our understanding is incomplete. The calculations for Big Bang nucleosynthesis are exquisitely detailed, relying on precise measurements of nuclear reaction cross-sections and the universe's expansion rate during that initial, frantic epoch. When we plug in all the known numbers, the models confidently predict how much lithium should have been created. The fact that ancient, metal-poor stars in the galactic halo consistently show only a third of that amount tells us that the error is not in the stars but in our theory. One leading explanation points to new, non-standard particle physics. Perhaps an unknown, exotic particle was present in the early cosmos, something like a lightweight cousin of the neutrino that interacted with nuclei and subtly altered the nuclear reaction rates, effectively destroying lithium as it formed. Another possibility lies not in the birth of the universe, but in the life of stars. Could these ancient suns be hiding the missing lithium? Some theorists propose complex mechanisms of stellar depletion, where lithium is dragged from the visible atmosphere down into the hotter interior and destroyed over billions of years. Observational campaigns have scrutinized these ancient halo stars, using the world's most powerful telescopes to measure their faint chemical fingerprints. The challenge is immense, as distinguishing a star's primordial lithium from any that might have been produced later requires finding the most pristine objects, fossils from a time before star death polluted the cosmos with new elements. This elemental puzzle is more than a minor accounting error. It is a direct motivator for new physics. The discrepancy is too large and too consistent to ignore, pushing scientists to consider everything from variations in the fundamental constants to the existence of decaying dark matter particles that could have disrupted the delicate nuclear chain. Does this mismatch between prediction and observation reveal a fundamental flaw in our story of cosmic dawn? Is the lithium problem a tiny, fossilized clue pointing to a richer, more complex physics operating in the universe's first breath? This struggle to balance the cosmic books for a single element forces us to look even deeper for other primordial anomalies hidden in the oldest light. The most detailed map of the infant universe should be a random splatter of hot and cold, a testament to primordial chaos frozen in time. Yet when scientists analyzed the data from the Planck satellite, they found a ghostly alignment that chilled them to the core. The largest fluctuations in the cosmic microwave background, the hot and cold spots from the dawn of creation, are not scattered randomly. They appear to be loosely but unmistakably aligned with the plane of our own solar system, a correlation so bizarre it was nicknamed the axis of evil. This large-scale anisotropy is a direct challenge to the cosmological principle, the foundational idea that the universe should look the same in all directions, with no preferred axis or special center. Cosmologist Joanna Dunkley has described the anomaly as statistically significant and deeply puzzling, forcing researchers to ask if they are seeing a real feature of the cosmos or some profound, unaccounted-for error in their data. The detection hinges on a complex statistical analysis of the CMB's multipole moments, which are essentially ways of breaking down the temperature map into components of different angular sizes. The lowest multipoles, representing the very largest scales in the universe, show this strange coherence, a preferred direction that seems to point directly at us. The Wilkinson microwave anisotropy probe first hinted at it, and the higher precision Planck mission confirmed it was real. The scientific community was thrown into a vigorous debate. Could this be something as mundane as foreground contamination, the faint glow of dust within our own Milky Way imperfectly subtracted from the data? Teams have worked tirelessly to rule this out, refining their models of galactic emission, but the alignment stubbornly persists. Other, more exotic theories have emerged. Perhaps it is evidence of a pre-inflationary universe, a relic structure from an era before the Big Bang that imprinted a preferred direction onto the fabric of space-time itself. Or maybe it indicates that our universe is not infinite and uniform, but has a complex, non-trivial topology, like a hall of mirrors on a cosmic scale. Researchers who first noticed the pattern described a sense of profound unease, watching as a cornerstone of their field seemed to develop a crack. The name itself, the axis of evil, reflects a mixture of dark humor and genuine concern. If this alignment is not an illusion, it means our entire observable universe has a subtle but real orientation, a cosmic north that points against all odds toward our own tiny backyard. Are we truly at the center of a cosmic coincidence, or is this a fundamental flaw in our understanding of universal homogeneity? Does this axis point toward a physics that operated before the inflationary epoch, a fossil from the true beginning of everything, or is it the ultimate cosmic illusion, a trick of perspective that will vanish with better data? The silent axis in the ancient light forces us to question whether our most basic assumptions about the cosmos are nothing more than a local custom. Our position in the galaxy is not a random address, but but a specific coordinate in a narrow band of safety. The Milky Way contains a galactic habitable zone, a theoretical annulus where the conditions are just right for complex life to persist. Earth orbits not only within our Sun's Goldilocks zone, but within this much larger, galactic-scale region of possibility. The coincidence is that we are perfectly placed, far enough from the dangerous, radiation-filled core to avoid sterilization, yet close enough to have been seeded with the heavy elements forged in generations of earlier stars. Astrobiologists point to two critical factors that define this zone: metallicity and stability. The outer rim of the galaxy lacks sufficient heavy elements, the metals needed to form rocky planets like our own. The inner galaxy, while metal-rich, is a tumultuous environment where nearby supernova erupt with devastating frequency, and the central supermassive black hole unleashes periodic blasts of radiation that could scour entire systems of life. Our solar system resides in a relatively quiet suburb, the Orion Cygnus Arm, a location that has afforded us a long, stable cosmic childhood. This timing is equally crucial. We exist during a period of relative galactic calm between more violent eras of rapid star formation and collision. The galaxy itself has a life cycle, and we have emerged during a mature, settled phase. The rate of catastrophic supernova events in our vicinity is low enough that life has had billions of uninterrupted years to evolve from single-celled organisms to complex, intelligent beings. Studies of exoplanet systems are now beginning to incorporate this galactic context, assessing not just whether a world is in its star's habitable zone, but whether that star itself is in the galaxy's habitable zone. A planet around a star in the chaotic galactic center, for instance, might have its atmosphere stripped away by gamma-ray bursts long before life could gain a foothold. Conversely, a world in the metal-poor galactic halo might not have even formed from the necessary rocky materials. This zonal alignment forces a profound reflection. Are we the beneficiaries of an incredible cosmic lottery, living in a privileged place and time that is exceptionally rare? Or is the Milky Way dotted with countless such oases, each with its own timeline of life and intelligence, separated by vast tracts of space and time? Our specific cosmic address, it seems, is written not just in our planetary conditions, but in the very architecture and history of our entire galaxy. Empty space is not truly empty. It is a quantum sea, a churning foam of virtual particles that flicker in and out of existence in a relentless, unseen dance. In this bizarre realm, mere motion can conjure reality from the void. If you were to accelerate through this vacuum, you would not simply feel a push. You would find yourself bathed in a warm glow of real particles, a heat born from your own motion. This is the Unruh Effect, a stunning prediction of quantum field theory that reveals a profound cosmic coincidence, a hidden thread connecting the physics of acceleration to the physics of gravity itself. The very same mathematics that describes this ghostly thermal bath for an accelerating observer also describes the radiation that should leak from a black hole, Hawking radiation. It is as if acceleration creates a kind of artificial event horizon, a boundary in space-time that makes particles appear. Physicist William Unruh, who first described this effect, captured its strange elegance, noting that the vacuum is not a state of nothingness, but depends on your state of motion. The connection is rooted in these horizons. For someone accelerating at a constant rate, there is a region of the universe from which light can never reach them, a personal cosmic blind spot. For a black hole, that blind spot is the point of no return at its event horizon. In both cases, the quantum fields that permeate space get tangled up at these boundaries, and that tangling manifests as real, detectable particles. The temperature of this radiation is incredibly faint for any acceleration we can achieve, making direct detection a monumental challenge. To measure the Unruh effect for even a modest acceleration, an observer would need a thermometer sensitive enough to detect a temperature of a mere 4 billionths of a degree above absolute zero. This has led scientists to a brilliant workaround, creating analog systems in the laboratory. They simulate the essential physics of an event horizon using other mediums. One powerful analogy uses flowing water. Researchers create a rapid flow in a water channel, a current so fast that ripples on the surface cannot travel upstream against it. This creates an effective horizon, a point where the flow speed exceeds the wave speed. Just as Hawking radiation predicts, experiments have observed the spontaneous creation of wave pairs at this artificial horizon, one trapped behind it and one escaping, a direct analog to the particle-antiparticle pairs at a black hole's edge. Other experiments use Bose-Einstein condensates, ultra-cold clouds of atoms behaving as a single quantum wave. By carefully manipulating these condensates, physicists can create sonic event horizons, points where the flow of the condensate exceeds the speed of sound. Any sound wave trying to cross this sonic horizon gets trapped, and just as the theory predicts, researchers have detected the sonic equivalent of Hawking radiation, quantized sound waves spontaneously generated at the boundary. These analog experiments are more than just clever demonstrations. They are testing grounds for the elusive theory of quantum gravity, providing tangible data where pure mathematics offers only paradox. The thermal nature of both Hawking and Unruh radiation suggests that temperature, acceleration, and gravity are deeply intertwined facets of a single, deeper reality. This theoretical synergy forces a radical question. Could the intense acceleration of the universe's first moments during the inflationary epoch have imprinted a thermal signature onto the very fabric of space-time, a ghostly heat that still echoes in the cosmos today? The quest to understand how particles emerge from nothingness by crossing an invisible line is leading us toward a unified vision of the cosmos, where the most violent and the most subtle motions in the universe are, in fact, two expressions of the same fundamental law. During a casual lunch at Los Alamos in the 1950s, physicist Enrico Fermi listened to optimistic chatter about interstellar travel and suddenly posed a devastatingly simple question. Where is everybody? His point was as sharp as a razor. The universe is ancient and vast, with billions of planets that could host life. If even a tiny fraction of those spawned intelligent civilizations, the galaxy should be teeming with explorers, their signals flooding the cosmos. Yet when we listen, we are met with a profound and unnerving quiet. This is the great silence, the 25th cosmic coincidence, a void of evidence that stands in stark opposition to our calculations of probability. The very tool we use to estimate the number of communicative civilizations, the Drake equation, seems to promise a crowded galaxy. It multiplies factors like the rate of star formation, the fraction of stars with planets, and the number of planets in the habitable zone. The equation then moves into more uncertain territory, the fraction where life actually appears, the fraction where that life becomes intelligent, and the length of time such a civilization releases detectable signals into space. It is in these final terms that the paradox likely resides. SETI researchers who have spent decades scanning the heavens describe a growing philosophical unease. The silence is not just an absence of data, it is a data point in itself. One compelling hypothesis is the zoo hypothesis, the idea that advanced civilizations are aware of us but have chosen to observe without interference, placing Earth in a kind of cosmic wildlife preserve. Another, more sobering possibility is that there is a great filter, an existential wall that every technological civilization eventually hits and fails to surpass. This filter could lie in our past, a step in evolution so improbable that we are truly alone. Or, more frighteningly, it could await us in the future, something inherent in technology that leads to self-destruction, whether through environmental collapse, nuclear war, or a runaway artificial intelligence. The vast interstellar distances themselves could be the answer. The speed of light may be an unbreakable barrier, making galactic empires impractical and isolating civilizations in islands of silence. Or perhaps technological progress leads not to expansion, but to a singularity, a transformation into a state we cannot recognize or detect, like beings that upload their consciousness into virtual realities, leaving the physical universe behind. The modern UFO debate and the discovery of countless exoplanets have only sharpened the paradox. We now know the planets are there, the potential cradles for life are abundant. But the signals, the artifacts, the visitors remain absent. This great quiet forces a profound reflection upon us. Are we the universe's first and only children, a fleeting spark of consciousness in an endless night? Or is the cosmos hiding its inhabitants, its elders choosing silence for reasons we cannot yet fathom? The silence is not empty, it is a question echoing back at us, asking what we will become, and whether we too are destined to join the great quiet. Every story you have ever read, every memory you have ever formed, is written in a language of information that the universe considers indestructible. According to the fundamental laws of quantum mechanics, information cannot be created or destroyed, only transformed. Yet, for decades, black holes presented a terrifying paradox, seemingly capable of the one thing the cosmos forbids, complete and utter erasure. Stephen Hawking first realized that black holes are not entirely black. Due to quantum effects at the event horizon, they should slowly leak a faint glow of radiation, now named Hawking radiation. This process causes a black hole to gradually lose mass and over eons evaporate completely. The paradox is stark. If a black hole vanishes, what happens to all the information about the stars, planets, or astronauts that fell in? Hawking argued that the radiation is purely thermal and random, carrying no information about the black hole's contents. Its evaporation would be a cosmic shredder, obliterating the universe's historical record and violating a cornerstone of physics. This ignited what Leonard Susskind called the Black Hole War, a fierce intellectual battle over the fate of information. The conflict strikes at the heart of our understanding, pitting the smooth, continuous geometry of general relativity against the discrete, probabilistic rules of quantum mechanics. One radical proposal to resolve the paradox is the firewall hypothesis. It suggests that instead of a smooth passage through the event horizon, an infalling astronaut would encounter a blistering wall of energy, a literal firewall that would vaporize them and their information instantly. This preserves information by preventing it from ever truly entering the black hole, but it shatters Einstein's principle of equivalence, the idea that free fall feels like floating in empty space. Another, more elegant idea is the ER equals EPR conjecture. This proposes that entangled particles, those spookily connected quantum partners, are physically linked by tiny wormholes in the fabric of spacetime. In this view, the particles that make up Hawking radiation on the outside remain intricately connected to the information trapped inside the black hole via these microscopic bridges. The black hole's interior and the exterior radiation are not separate, but one entangled system. When the black hole evaporates, the information is not lost, but transferred and encoded in a fiendishly complex way within the outgoing radiation. This hints at a holographic principle. the mind-bending idea that all the information describing a three-dimensional volume of space can be encoded on its two-dimensional boundary, much like a hologram on a credit card stores a three-dimensional image. For a black hole, this means every bit of information about what fell in is painted in a scrambled quantum code on the surface of its event horizon. Gravitational wave observatories like LIGO and Virgo are now providing new ways to test these ideas. The ripples in spacetime from colliding black holes carry their own information about the event horizons involved, offering indirect clues about how information might be preserved. String theorists use complex mathematical models to show how information could escape during the evaporation process, while others look for subtle signatures in the precise spectrum of Hawking radiation itself. If information is truly preserved, even after being stretched and squeezed beyond the edge of spacetime, what does that tell us about the fundamental nature of reality? Does it mean that our perception of a smooth, continuous universe is an illusion, and that at its core, existence is a vast, interconnected network of quantum information? The black hole information paradox forces us to confront the possibility that spacetime itself is emergent, a secondary phenomenon that arises from something deeper, something built from pure information. The trigger for cosmic inflation remains one of the most profound puzzles in all of science. For this exponential expansion to have begun, the universe must have been in a very specific, high-energy state known as a false vacuum. This state was inherently unstable, like a ball perched perfectly at the crest of a hill, and its decay into a lower energy state released the colossal energy that drove inflation. The profound coincidence is that this process required an exquisitely fine-tuned set of initial conditions to start, to last long enough to create our vast cosmos, and then to stop gracefully. Cosmologist Alan Guth, who pioneered the theory, highlighted this fine-tuning problem, noting that the parameters of the inflationary field had to be set with incredible precision. If the process had ended too quickly, the universe would have remained microscopic and featureless. If it had lasted too long, space would have been stretched into a near-perfect void, with matter and energy spread too thin for galaxies to ever form. The fact that inflation lasted just long enough to produce a universe with the smoothness and structure we observe feels like a cosmic adjustment of breathtaking accuracy. This leads directly to the mind-bending concept of eternal inflation. In this model, once inflation starts, it never truly stops everywhere. The decay of the false vacuum is not a uniform event, but occurs in localized patches like bubbles forming in a pot of boiling water. Our entire observable universe is just one such bubble that happened to stop inflating, allowing for the formation of stars and planets. Beyond our bubble, the inflationary background continues to expand exponentially, constantly giving birth to an infinite number of other bubble universes, each with potentially different physical laws and constants. This is the multiverse in its most concrete cosmological form, the incredible predictive success of inflation, confirmed by the detailed temperature variations in the cosmic microwave background mapped by the Planck satellite, gives the theory immense credibility. The patterns in that ancient light match the predictions of inflationary models with remarkable fidelity. Yet, Planck's data has also constrained the theory, ruling out many of its simplest versions and forcing physicists to consider more complex scenarios. This success brings its own set of philosophical challenges, such as the measure problem. In an infinite multiverse, everything that can happen will happen an infinite number of times. How do we define probabilities or say that any one outcome is unlikely? Furthermore, string theory suggests a landscape of vacua, a vast array of possible stable states for the extra dimensions it proposes. Eternal inflation would then populate this landscape, creating a multiverse where every possible set of physical laws is realized somewhere. Did our specific, life-giving universe emerge from a random quantum fluctuation in an eternally inflating meta-universe, a statistical inevitability in an infinite ensemble? Or does the need for such precise initial conditions point to a deeper cause, a fundamental law, or even a conscious choice that set the entire cosmic drama in motion? The mystery of inflation's beginning is ultimately a question about the origin of existence itself. The precise tuning of the universe's fundamental dials feels less like a random draw and more like a carefully calibrated setting for life. If the force of gravity were even slightly stronger, the cosmos would have collapsed back on itself in a fiery crunch moments after the Big Bang. A fraction weaker, and matter would have flown apart too quickly for galaxies to ever coalesce. This is not an isolated example. The strength of the nuclear forces, the mass of the electron, and the value of the cosmological constant all reside within a breathtakingly narrow window of possibility. The cosmological constant, which governs the acceleration of the universe's expansion, is so exquisitely balanced that a change of just 1 part in 10 to the power of 120 would render the cosmos uninhabitable. A slightly larger value would have ripped apart proto-galaxies before they could form, while a smaller one would have caused the universe to recollapse long before life could emerge. This staggering array of perfect numbers is the heart of the Anthropic Principle, an idea articulated by physicist Brandon Carter. He distinguished between its weak form, which simply states that we must be prepared to observe conditions compatible with our existence, and its strong form, which suggests the universe must have properties that allow life to develop within it at some stage. The weak principle is a simple statement of selection bias. We are here, so the universe must be one that permits observers. The strong form, however, ventures into more controversial territory, hinting that the laws of nature themselves are in some sense necessitated by the requirement for conscious life. To grasp the sheer improbability, particle physicists run simulations of alternative universes. In a cosmos where the strong nuclear force is just a few % stronger, hydrogen would be unstable and stars would never shine. If the mass difference between a neutron and a proton were minutely different, the delicate chain of nuclear fusion that builds the elements of life would be broken. We would be left with a universe of hydrogen, or one devoid of the complex chemistry that forms planets and people. These are not minor adjustments, they are cosmic deal breakers. This profound fine-tuning forces a monumental question upon us. Is our universe a solitary, incredible accident, a one-in-a-Googleplex fluke that just happened to produce us? Or does the Anthropic Principle find its most natural home in a multiverse, an infinite froth of bubble universes, each with its own random set of physical constants? In such a vast ensemble, it is no surprise that we find ourselves in one of the rare, life-friendly bubbles, our existence merely a product of unimaginable cosmic statistics. For some, however, this multiverse explanation feels like a retreat, a way to explain away the enigma rather than solve it. They see the precise alignment of these 29 coincidences not as a statistical inevitability, but as a signature, a hint of a deeper logic or even a deliberate architecture woven into the fabric of reality. Does our ability to observe and ponder these constants itself point to a universe that is not merely hospitable, but in some profound sense meant to be understood? The Anthropic Principle does not answer this, but instead holds up a mirror, forcing us to confront our own place in a cosmos that seems improbably, and perhaps intentionally, aware of our presence. A galaxy spins like a carousel of fire, but its outer stars are moving far too fast. According to the laws of gravity, these distant stars should be lagging, slowing down as they orbit far from the galactic center, just as Pluto moves more slowly around the Sun than Earth. Yet when astronomers measured their speeds, they found something astonishing. The rotation curves remain flat. The stars on the edge race along just as quickly as those near the core, held in their paths by a gravitational grip that the galaxy's visible mass simply cannot provide. This profound discrepancy is the 29th cosmic coincidence, and it forced science to confront an invisible reality, dark matter. Astronomer Vera Rubin, whose meticulous work on galaxy rotation cemented this discovery, reflected that the discrepancy was immediately obvious, and in a good universe, one would then know what it is. But we do not. Her observations revealed a universe dominated not by the stars and gas we see, but by something we cannot. The dynamics of a galaxy are a cosmic tug of war between the inward pull of gravity and the outward tendency of objects to fly off in a straight line. The speed at which a star orbits is a direct measure of the total mass inside its orbit. For our solar system, almost all the mass is in the Sun, so the planet's speeds drop predictably with distance. In a spiral galaxy, if all the mass were in the bright disk of stars, we would see the same rapid drop-off. Instead, the flat rotation curves tell us that the enclosed mass increases with distance far beyond the visible edge, implying a vast, invisible halo of matter enveloping the entire galaxy. This dark matter does not emit, absorb, or reflect light, interacting with normal matter almost exclusively through gravity. Supercomputer simulations of cosmic structure show that this dark matter is essential, its gravitational scaffolding guiding the formation of galaxies and the intricate filaments of the cosmic web. Some physicists have proposed an alternative, that our understanding of gravity itself is incomplete. Modified Newtonian dynamics, or MUND, suggests that the laws of gravity change at very low accelerations, like those experienced in the outskirts of galaxies. This tweak can indeed reproduce the flat rotation curves for many spiral galaxies without invoking dark matter. Yet this alternative faces its own profound challenges. When two galaxy clusters collide, as seen in the Bullet cluster, the visible gas, hot and glowing in X-rays, smashes together and slows down. Meanwhile, the bulk of the mass, mapped by gravitational lensing, sails right through the collision, completely separated from the normal matter. This is a direct, visual demonstration that most of the mass is dark and collisionless, a behavior that modified gravity struggles to explain without still needing some form of unseen matter. So we are left with a ghostly substance that makes up over 85% of the universe's matter, a substance that shapes the largest structures in the cosmos, yet remains utterly invisible to our most powerful detectors. Countless experiments deep underground in abandoned mines and mountains have searched for the faintest whisper of a dark matter particle colliding with ordinary matter. So far, the silence is deafening. What is this substance that holds galaxies together with an unseen hand? Is it a sea of exotic, slow-moving particles left over from the Big Bang, or could it be something even stranger? A relic from a different dimension or a shadow of a more complex reality. The rotation of every spiral galaxy is a silent testament to a mystery that surrounds us, a final, fundamental enigma written in the motion of the stars. Ancient Babylonians meticulously tracked the wanderings of planets against the fixed stars, seeing in their celestial choreography the direct hand of gods shaping human destiny. For millennia, humanity has looked upward and found intention in the sky's geometry, interpreting planetary alignments and eclipses not as chance but as divine messages. This deep-seated need to find meaning in cosmic patterns is the very engine that has driven our scientific understanding forward. The Greek astronomer Ptolemy, for instance, crafted an entire Earth-centered universe of perfect circles and complex epicycles to explain the seemingly irregular paths of the planets, a model that held sway for over 1,000 years because it imposed a beautiful mathematical order on the heavens. Historians of science note that it is often the stubborn anomalies, the data points that refuse to fit the established order, that spark the greatest revolutions. The story of Uranus is a perfect example. After its discovery, astronomers calculated its future path, only to find it consistently strayed from its predicted course. This tiny irregularity, this cosmic coincidence that the math did not work, could not be ignored. Rather than dismissing it, they dared to propose a radical solution: that the gravitational pull of an unseen eighth planet was tugging on Uranus. Using nothing but Newtonian mechanics and the power of prediction, Urbain Le Verrier and John Couch Adams independently calculated where this hidden world should be. When astronomers pointed their telescopes to that precise spot in 1846, they found Neptune, a planet revealed by a glitch in another's orbit. This was a paradigm shift, proving that the universe could be understood not just by what was visible, but by the subtle, invisible forces revealed through coincidence. Each leap in our tools has expanded the scope of these mysteries. The invention of the telescope unveiled moons and rings, while particle detectors later exposed the ghostly realm of the quantum. Consider the orbit of Mercury. For centuries, its path around the Sun presented a tiny, persistent flaw, a slow wobble in its closest point to the Sun known as the precession of its perihelion. Newton's gravity could not fully account for it. This minuscule discrepancy, this one planet's imperfect dance, became a crucial test for a new theory of gravity. Einstein's general relativity, with its vision of mass warping spacetime, perfectly explained the anomaly, turning a celestial misfit into a triumphant confirmation of a new cosmic order. From the first astrologers charting omens to the physicists probing the holographic principle, our journey has been a continuous reinterpretation of the sky's whispers. How will future generations view the 29 puzzles we grapple with today? Will our unexplained alignments and dark flows be seen as the trivial quirks of a limited perspective, or will they be remembered as the first faint tremors of a scientific revolution we are only now beginning to imagine? The cosmos is a tapestry whose threads are woven from mystery itself. Look closely, and you will see the same patterns emerging across vastly different scales, from the quantum flutter of a neutrino to the silent flow of galaxy clusters. These 29 coincidences are not isolated curiosities, but recurring motifs in a grand design we are only beginning to trace. They cluster around a few profound themes, a hidden grammar of the universe that speaks of fine-tuning, of inexplicable alignments, and of fundamental pieces missing from our puzzle. As cosmologist Martin Rees has reflected, our universe seems strangely hospitable to life, its laws and constants appearing suspiciously well adjusted. This puzzle forces a conversation that spans astronomy, particle physics, and philosophy, demanding we look at the whole picture. One dominant theme is the ghost in the machine, the influence of unseen components. Dark matter provides the gravitational skeleton for the cosmic web, explaining flat galaxy rotation curves and the immense pull of the Great Attractor. Dark energy, the force behind the universe's accelerating expansion, dictates the ultimate fate of these vast structures and the growth of the great voids. Another theme is the eerie harmony of numbers, from the precise value of the fine structure constant that allows for chemistry, to the Fibonacci spirals in galaxies and seashells, suggesting a deep mathematical order underpinning all of reality. Then there are the structural patterns, the cosmic architecture that defies randomness. The alignment of quasars in vast filaments mirrors the strange, large-scale axis seen in the cosmic microwave background, the so-called axis of evil. The Great Silence and the Fermi Paradox present a different kind of pattern, a statistical and sociological mystery woven into the apparent abundance of planetary real estate. Even the fleeting visit of Oumuamua fits here, a pattern of one, hinting at the diversity of interstellar travelers we have only just begun to sample. When you place these anomalies side by side, a compelling narrative emerges. The same vacuum energy that drives cosmic inflation may be connected to the dark energy we measure today. The quantum entanglement that saves information from black holes might be related to the Unruh Effect, linking the physics of the very small to the physics of immense gravity and acceleration. Are we seeing scattered pieces of a unified theory, a single framework that can explain the infant universe's smoothness and the modern galaxy's rotation with one elegant set of equations? Or are these patterns merely the scars of a chaotic and random origin, the lucky arrangements that survived a tumultuous birth? This analytical thread, connecting one mystery to the next, prepares us for a final synthesis. It invites us to ask not just what these coincidences are, but what they collectively mean for our place in a cosmos that seems, against all odds, to be both knowable and deeply, wonderfully strange. These 29 cosmic coincidences, from the Moon's perfect eclipse to the ghostly pull of dark matter, form a single, resonant message. The universe is not quite as random as we once believed. Each anomaly, whether a precise number like the fine structure constant or a colossal structure like the Great Attractor, chips away at the edges of our current models, revealing the outlines of a deeper reality we have yet to comprehend. The overarching themes are impossible to ignore: a universe that appears exquisitely fine-tuned for complexity, a cosmos dominated by hidden forces we cannot see, and a persistent hum of mystery that underscores the limits of our current knowledge. This is not a failure of science, but its very engine, driven by humanity's enduring and insatiable curiosity. We have always looked to the stars and seen not just points of light, but reflections of our deepest questions. Albert Einstein once captured this sentiment perfectly, reflecting that the most beautiful experience we can have is the mysterious. It is the fundamental emotion that stands at the cradle of true art and true science. This sense of wonder is our birthright, a call to keep looking, keep questioning, and keep building better tools to listen to the cosmos. The journey does not end here. Tonight, step outside and simply look up. Trace the familiar constellations and remember that within that vast darkness lie puzzles like the Wow, Signal, and the Axis of Evil, waiting for their solutions. Follow the latest data from the James Webb Space Telescope as it peers into the cosmic dawn. The greatest discoveries are still ahead of us, hidden in the next decimal point of a measurement or the next faint whisper from the void. If these enigmas have sparked your curiosity, subscribe for more deep dives into the wonders of space and time. And we would love to hear from you. Which of these 29 cosmic coincidences left you the most astonished? Share your favorite mystery in the comments below, and let's continue this exploration.